Welcome back. This time around we're going to take a look at the Spectravideo 80 column card, which you might remember we tried to do in a previous video, but ended up fixing the super expander instead. So yeah, let's get into it. So the Spectravideo 80 column card is based around the Hitachi 6845 CRTC controller chip. This was actually made by other manufacturers as well. I think Rockwell, Motorola, and maybe a couple of others. This is the same chip that was used in the BBC Micro, the Amstrad CPC, and even some of the early IBM compatible video cards. The datasheet will tell you it's designed to address 16 kilobytes of video memory, but the BBC in particular did some creative external logic hackery to get it to address 20 kilobytes of video memory. Over here, we've got our character ROM. So this has got the individual bitmaps for each character, all 256 of them. And as we'll see later, there's 16 bytes per character in this ROM. Over here in the middle is the 2 kilobytes of static RAM. This is the video memory that's used by the CRTC and accessed by the main processor as well. Each one of these chips is 1 kilobit by 4. So you need 4 of them to make the 2 kilobytes. Over here is our multiplexers that multiplex the access to the video memory between the CPU and the CRTC, because they both need access. The main processor needs access to update what's on the what's going to be displayed on the screen, and the CRTC needs access to actually display it. And yeah, there's various other bits of glue logic that latch things and control access and decode signals and so on. So we'll have a quick look at that in the schematic in just a moment. Okay, so we're looking at the multiplexers here that control the access from the host CPU and the CRTC. And we can see over here we've got the CPU address lines, the CRTC address lines, and so on down here. And the multiplexers are just controlling, based on the multiplex signal, which set of address lines are actually driving the RAM chips. And this is our 2 kilobytes of static RAM. Each IC is 1 kilobit by 4, which is evidenced by the address lines being A0 to A9. That's the number of bits you need to address 1024 locations, each of which is storing 4 bits, which we can put out into these latches over here. So moving over, we can latch our data into the latches here, and that provides an offset into the character ROM. So we've got address lines 4 through 11 hooked up to the character latches, and that allows us to select multiples of 16 bytes in the ROM. So character number 0 starts at location 0, character number 1 will start at location 16, number 2 at 32, and so on. And then down the bottom here, we've got the 4 address lines that come from the raster outputs on the CRTC. And this is what drives the individual scan lines for each character, which is just an offset within those blocks of 16 characters in the ROM. So this part of the logic decodes the access to the I/O area by the processor. This is the I/O request from the processor. And the decoding here is, in a nutshell, setting the chip select for the CRTC for I/O port 50, and by adding the A3 we get 58, and that causes, in conjunction with bit 0 here of the data bus, causes us to raise the enable signal for the video memory. And if we head over here, you see if we're doing a memory request over here, combine that with our input from that we looked at just a second ago, when we've decoded port 58 and data bit 0 to get the banking or bank select bit, combine that with the address bits, and we end up, in a nutshell, getting a RAM disable signal, which goes across the bus to the host computer to disable the RAM, and then we get a video RAM enable signal. So the idea is that when we're accessing the region of memory occupied by the video RAM, we get a video RAM signal goes high, and at the same time we get a RAM disable, which would appear to go low at the same time because they're the inverse of each other. So what we see here is a variation on a little basic program that was posted on the Spectravideo Facebook group, and it's resetting the first 12 CRTC registers in an attempt to provide a better and more stable image, apparently on PAL televisions. I'm not quite sure how these values differ from what Disk Basic uses normally, but I know from looking at the CPM source code I found online, these are the exact same values in that CPM source. So we'll have a bit of a look and see what difference it makes. So first up, side by side, we're looking at what used to be a little Sony security monitor that's got the 80 column output on it. And using the little basic program, which is the image on the right, actually seems to introduce some flicker to the image. The image on the left is the standard stock Disk Basic disk that I've got, and the one on the right is the one after running this little program. So it certainly in the PAL region where I am with this little monitor, these register settings make the image worse. And maybe that varies from monitor to monitor. So maybe if I tried it on an old CRT TV, maybe the outcome would be the opposite. So this time around, I'm looking at the Samsung TV, LCD TV that I normally use with the Spectravideo. And on the left is the image with the standard Disk Basic. And the background is a little bit flickery and horrible. But on the right, same TV, same system, after running the little basic program to adjust the CRTC registers, the image is much, much better. So clearly it is a benefit for an LCD monitor. And again, like the CRT, maybe the results vary from LCD monitor to LCD monitor. I don't know. I can only go by what works on the hardware that I've got. I haven't really been through all of the CRTC registers and the sorts of things you can do with them, but two of the registers in particular, registers 12 and 13, deal with the start address in the video memory that the CRTC will start generating the image from. And systems like the BBC Micro, and I don't know about other systems that use this 6845, but certainly the BBC Micro, use this to do hardware scrolling in a lot of games. I checked the source code for CPM on the Spectravideo. It seems to do its scrolling just by basically moving all the characters around in memory rather than using the hardware scrolling. So I thought I'd do a little experiment to see if the hardware scrolling actually worked. So a little basic program like this, it's pretty rough. It's sort of evolved a bit over time, but we start off with variable P, which is our horizontal position. Yeah, I could have used H, but as I say, it evolved over time. So P is our horizontal position, V is our vertical position in lines, and then we create a byte offset from the start of the video memory, which is the horizontal position plus the vertical position times 80, because 80 characters to a line. Then at line 101, if we happen to have run off the end of video memory, the 2048 bytes, then we just wrap ourselves back around to the start. In practice, that shouldn't happen because of our if statements between 40 and 56, but it's in there just in case. Line 110 and 120 calculate the low and the high byte respectively of the start address of screen memory, and then lines 130 and 140 put the high byte into register 12, and 150 and 160 put the low byte into register 13, and rinse and repeat. It's not the cleanest bit of basic code, but it demonstrates the concept. So if I run this, and noting that our keys are A, S, Z, and W, I can't remember quite how I came up with those, but anyway. So if I press A, we can scroll sideways. And the rubbish that's appearing at the bottom here, that's basically because I'm not clearing the memory that's scrolling onto the bottom of the screen. I can't do that from BASIC because banking the video memory in clobbers the area that BASIC uses for some of its workspace. So if I try and do it, it'll crash BASIC. From machine code, I could do it. And press the S key and we scroll right. And what have we got? Z and W. So W, we can scroll up. And Z, we can scroll down. So the CPM BIOS could actually do some pretty quick vertical scrolling using this technique if they'd written the code to do it. I don't know what Disk Basic does, but I suspect it does it the same way as CPM, basically by moving the memory, using the processor to move the memory around. But yeah, in that case, BASIC could benefit from using the hardware scrolling too, which is, as I say, exactly what the BBC Micro does. And I'm guessing the same technique probably works on other systems that use the 6845. So yeah, I suppose you could use it for doing some funky text-based CPM games or something. I don't know, but it's just something for fun and a bit of experimentation. So there we go. Now, something I did neglect to explain during that scrolling demonstration was that this works because the video chip only has access to 2 kilobytes of memory. So if we tell the video chip to start at 1 kilobyte as its starting location, it gets to the end of the 2 kilobytes and the addressing just wraps back around to the start. So that's why that works. The other important thing with that demo and with the way the video works in general is the processor sees the video RAM at F000 to F7FF, but the CRTC sees it as 0000 to 07FF. So when we're programming registers 12 and 13, we need to program it with the addresses that the CRTC sees, not that the system CPU sees. So that's why when you look at the code, you might be thinking, why is he starting with an offset of 0 for position? So X and Y 00 on the screen, why is that a byte offset of 0? Because that's not where the video memory is. Like, that's where the CRTC sees the video memory, not where the Z80 sees it. So important distinction there. So if I was writing code that was updating the screen memory from the computer itself, my Z80 code would have to reference the video RAM at F000 upwards, but the CRTC sees it starting at address 0. So that explains that discrepancy in case you're wondering. So that pretty much wraps up our quick look at the Spectravideo 80 column card. It's sort of a relatively high level overview of how the card works and some of the things you can do with it. If you enjoyed that, feel free to subscribe and click the like button. That feeding the YouTube algorithm like that keeps it happy. And yeah, maybe we'll see you on the next one. Cheers.